In this video, we're going to talk about the uncertainty propagation problem. So what you basically have is you have identified everything that is uncertain in your model, in a physical model, and you have quantified this uncertainty using probability statements, and then you would like to propagate this uncertainty through the physical model to characterize your state of knowledge about quantities that this physical model predicts. So let's study this through an example. Consider here a trailer driving on a bumpy road, and first of all we're going to come up with a model for the frequency and the amplitude of the trailer suspension. So let's say that the trailer has mass m, the suspension has a spring constant k. We're going to ignore any damping effects. Of course, this is unrealistic, but for the sake of this example, it's going to be okay. Now v is going to be the velocity with which the trailer is traveling on the bumpy road. Y naught is the amplitude of road roughness. So here we're going to assume that the road goes up and down in a sinusoidal way, with Y naught being the amplitude and L being the wavelength of the road roughness. Now, if you draw the free body diagram of the trailer and you do a little bit of dynamics, and you get the differential equation that describes the oscillations of the spring, you're gonna get that the angular velocity of the spring is 2 pi times the velocity of the trailer divided by L. And if you work out what the maximum amplitude of the oscillation of the spring is going to be, you will find that is the absolute value of k times y naught, where y naught is the amplitude of the road roughness, and divided by k minus m omega square. So this is all trivial, and you can find it using basic dynamics. Now, let's take this. This is our model essentially that tells us what the angular velocity and what the angular frequency and what the amplitude of the oscillation of the spring is going to be. And it is a causal model, and we can arrange it in a graph so that its causal structure becomes apparent. So this is the graphical interpretation of what is found in these equations. So you see that v, the velocity, and the velocity with which the trailer is traveling, and the wavelength of the road roughness together conspire to give you omega. And then if you have the spring constant and the mass of the trailer and the amplitude of the road roughness and the angular frequency omega, then all these four together will give you the maximum amplitude of oscillation. So now this is our model, and this is the causal interpretation of our model. This is how the quantities of interest omega and x get their values. Now the next step is to quantify our state of knowledge about the end nodes of this graph. So we need to go over each one of the end nodes, over each of the nodes that have no parents, and basically say what we know about them. So if we go to k, for example, it's a spring constant. We're probably dealing with a specific spring which we bought from somewhere, and we go and ask the manufacturer what is the spring constant, if you don't want to measure it, of course. And they tell us that I can guarantee that the spring constant is between this and that value with very high probability. And this is given in this table right here as the first entry. So the spring constant, we know that's going to be between 159,000 999 Newton meters up to 160,001 Newton over meter. And we do the same thing for all other quantities. For example, for the velocity with which the trailer is traveling, v. That's essentially this depends on the driving habits of people, and let's say that it's going to be anywhere between 80 and 150 kilometers per hour. Now, about the loading condition, m, the mass that the trailer carries, we know that the trailer itself, let's say, is 100 kilograms, and then a driver may put on it another 100 kilograms. Maximum of they may put on it maximum another 100 kilograms. So m, the mass of the trailer, could be anywhere between 100, which is its own mass, up to 200 kilograms, which is the mass of the trailer plus the mass of the load. Now, about the road condition, the amplitude the amplitude of the roughness, I have picked it to be anywhere between 0 and 100 millimeters, and the road condition, the wavelength of the road roughness, pick it to be anywhere between 1 and 2 meters. Of course, this is completely arbitrary right now. If you had a real problem, you would have to think a little bit more deeply about these choices, and they will have to accurately represent what you know about each one of these variables. Now, what I want you to notice is that I haven't really said anything about x and omega, because x and omega are derived quantities, they're not basic quantities. X and omega are caused by all the other variables. So I just went over the variables that are basic, and I describe my state of knowledge about them. Now that we have quantified our state of knowledge about all these unknown variables, what we need to do is propagate this uncertainty through the causal model to characterize our uncertainty about any quantity of interest. And here, these quantities of interest are going to be x and omega. And this is the way we can propagate uncertainty through a model, is through Monte Carlo sampling. And it is quite straightforward. All you do is you sample random inputs many times. So you have, for example, the mass of the unknown mass of the trailer being between 100 and 200 kilograms. You go and you sample uniformly between 100 and 200. And you do that simultaneously for all the variables that you are uncertain about. And then you evaluate, for each one of these samples, you evaluate the model outputs on these inputs, and you can estimate any statistical interest in this way. And we're going to learn about Monte Carlo in detail. We're going to devote 2 lectures on Monte Carlo, but just the simplest thing that you can do, with which I'm assuming that you are kind of familiar, you have seen histograms in the past. I'm just going to show you a histogram. So through this process of sampling random inputs and evaluating the important outputs of your model, you can draw histograms of the important outputs of your model. For example, here you see a histogram of the angular velocity omega, and you see a histogram of the amplitude of the oscillation x. And these histograms represent your uncertainty about these 2 quantities as induced by your uncertainty about the basic inputs of your model. So this is basically how your uncertainty about the basic inputs translated into uncertainty about derived quantities through propagation through the model.